Greetings everyone. We're going to be talking about force and free body diagrams. Here we have a cup sitting on my desk and I'm pushing it with my finger. With some amount of force, we could just call that magnitude Fa. I know that the cup is pushing back on my finger because of how it's deforming my finger right here. We're going to talk more about what is this magnitude of the force that the cup exerts back onto my finger, and how to draw these free body diagrams. So first, let's talk about forces. So when we talk about force, we need to know what matters when we talk about force. Basically, force equals what? What matters? First we can consider is that we have some grass down here, and what happens if we fall on the grass. And hopefully we were able to support ourselves with our hands. So what's going to matter when you fall into the grass? What's going to hurt more or hurt less when you fall in the grass? So one thing that will matter is what was that change in velocity? So basically, after you hit the grass, your velocity is going to be 0, or it's going to stop you pretty quick. And then how far up you were when you fell. If you fall from a very short height, maybe you're not hurt, but you know if you fall from a tree, you could get hurt very badly. So the bigger delta V is going to give you a bigger force. So we could just write this like this. It's going to imply that force is greater. All right. So another thing is that children are a lot more resistant to falls than adults are, and part of that is because of the mass. And you could work this out too, is like you could put on a backpack or whatever, and then you fall down, you know that you're more likely to get hurt. So having more mass means that you're also more likely to get hurt. So whatever force you feel that might be hurting you from the ground is a force that the ground is exerting onto you. So greater change in velocity, greater mass, both give you greater force. So another thing I'd like to contrast this out with is maybe, what if instead of falling on grass, you fell on a sidewalk? So in this case, now you're falling on a sidewalk. So why does the grass end up hurting you more than the sidewalk if just you tripped and fell? Well, one of the reasons could be because the grass is more squishy, sidewalk is not squishy. So what that squishiness means is that it's going to take more time in order to slow you down. And we worked these out in these kinematic equations where we talked about acceleration, and if you have a shorter time, then your acceleration has to be bigger. And this is directly related to the force that you're going to feel also. So basically, the smaller delta t that you have, the greater the force. So this one is a bit different than these other two. Whereas we're increasing mass, increasing change in our velocity, gives us greater force. But here, when you have smaller delta t, you're going to have greater force. So one thing that we know is that momentum is mv. So we could write out what is our change in momentum. So your change in momentum, hopefully your mass isn't changing as you fall down. It's just going to be m delta v. So what if you wanted to talk about force? So here we wanted force to be bigger when mass got bigger, and bigger when delta v got bigger. So both of these are the case, are going to be linear, so m delta v. So as m gets bigger, delta v gets bigger, force gets bigger. But here, when delta v gets smaller, delta v gets bigger. So what that means is you need to put that on the bottom. So it's inversely proportional. So here we have m delta v, delta t, or we could do delta p, delta t. And since we're doing deltas here, we really should write F average to be technical. And force is a vector, so is velocity. and so is momentum. So now here we have force average is equal to delta P, delta T, or we could write it out in derivatives, dp dt. So let's talk about Newton's three laws. So the first law is that with no net external force, objects continue to remain at rest or at a constant velocity. So let's just first imagine maybe some ball on my desk, and if I observe it for some time, the ball will not change its location. It will always remain right there. I can come back an hour later, the ball will still be there. As long as my desk is level, whatever, the ball is going to remain at rest. Unless there's some net external force. So maybe something got pushed. Maybe the ball got pushed, and then the ball will not remain at rest. It will accelerate and move away. So this first part is pretty easy to conceptualize. So whatever remains at rest will continue to remain at rest. And this speaks well to our experience. And this other part is no net external force. So this net part is a crucial part here, because I could have, instead of the ball here, I could push on the ball this way, and you could push on the ball with an equal amount of force on this side. And if we both push with the same amount of force, the ball will not begin to move. It will still remain at rest. And that's easy to realize too. You could also imagine a tug of war, a bunch of people pulling on a rope. This guy's pulling this way, this guy's pulling this way, and if they both pull with the same amount of effort, same amount of force, then neither one of them will move anywhere. You can watch the little flag here, and nothing is moving either way until one of them starts pulling a lot harder, or gets tired, and then the system will start to move. So as long as the forces are equal, then the object will not move. So the net external force means that this has to be unbalanced in some way. And that can be the case of the tug of war too. But the second part is the not so intuitive part. Here we have or at a constant velocity. So what this is telling us is that if I roll a ball, over the grass or something, so this ball is I'm going to give it some velocity. I'm not going to touch it anymore. The ball is rolling. What this says is that the ball should just keep rolling forever at this constant velocity. But this does not speak well to our experience. We know that the ball slows down. We know that it eventually comes to a rest. We know that objects don't continue at a constant velocity. So what is going on here? Well, these two guys, Galileo and Newton, both had some incredible insight here, in which they could imagine a reality that there was no friction, basically. No air resistance, no friction with any surfaces. And from that, they were able to extrapolate back to this first law, basically. So what's causing the ball to slow down is that there is some force on the ball. And that's this force of friction from the grass here. We could throw a ball through the air. And what's happening is that the ball is actually hitting these air molecules and giving away its momentum to these air molecules. And that's what's slowing this ball down. So in each of these cases, there's some kind of net force in which is slowing these objects down. The second law is that a net force causes a change in the momentum. So this is realized by F equals ma, which we could also write as this dp dt. And we'll show that these two are the same. So the first law is actually a consequence of this second law. So if we had no net forces, then the momentum of an object was constant. So let's just write this out. 0, no net forces, 0, is dp dt. So this is going to give us, P final is going to be equal to P initial. So if there were no net forces, then the object's momentum would be constant. But this tells us that if there is a net force, this tells us how the object changes its motion. So this is an important thing here, is that this ma, and that this is how an object's acceleration is proportional to the force that's being acted on the object. So real briefly, let's just have some box here. Let's say that it's 10 kilograms. Let's say that we push it along on ice or something like this. And we push it with a force of 100 newtons. Now, Newton is the unit of force, and it's equal to kilogram meters per second squared. So you can get that here. M is kilogram, acceleration is meters per second squared. And we named this unit after Isaac Newton. So here we have that the force is equal to ma. So if we have a 100 Newton force to the right, we could just write that I hat is going to be m, so that 10 kilograms, and then now times a, whatever direction a turns out to be. So now we're going to divide both sides by this 10, and so then we're going to get 10 meters per second squared. I hat is a. So this is two important concepts. One is that the acceleration is proportional to the force by the object's inertia, the mass of the object. Not the weight of the object. The weight deals with how that object feels under gravity's influence. The mass of an object is how much stuff is there, and that's represented by this kilograms. That's the object's inertia. So is that the inertia times the acceleration is the force. And the other important part is that this acceleration is in the same direction as the force. It may seem pretty intuitive. You push on this box, it's going to go in that direction. What other choice does it have? So the other thing that we could explore is, what if we now pulled with 200 newtons of force? So now we could try 200 newtons. It's going to be 10 kilograms. And so then our acceleration is going to be 20 meters per second squared. So if you pull with twice as much force, you get twice the acceleration. The third law is one that you may be pretty familiar with, or at least have heard it in some context. That's that every action has an equal and opposite reaction. So here we're going back to the cup on the desk. I'm going to push on the cup, and the cup pushes back on my finger. I know that the cup pushes back because my finger is not normally flat. And if you look closely here, you'll see that my finger has deformed. There's now a flat part of my finger here. The cup is pushing back on my finger, making it that shape. So you could try this out. You could try pushing on your desk or on something heavy, and you can feel that that thing is pushing back on you. And so this is the third law. However hard you push on something, something else is going to push back on you with the same force. So another way that you can imagine it is, what if you stand on the beach? If you're standing on the beach, what ends up happening is that you make a nice footprint in the sand. You know that you are being pulled down by gravity. So there's your weight. We'll later learn that that's m times g. So this is the force of gravity on your body. You're being pulled towards the center of the earth. And you're not accelerating down through the sand towards the center of the earth. You are remaining stationary. And the way that that happens is that the sand ends up pushing back onto you with an equal and opposite force. So that opposite part is the opposite direction. The equal is the magnitude of that force. So here we have a 10 kilogram object that's going to be acted on by two forces. We don't know what these forces are. So let's go ahead and draw this out. And we have two forces on it. So one of the forces is acting on it towards the north. Well, we could draw that this way. And this is a 20 Newton force. The object is accelerating with an acceleration of 1.0 meters per second squared to the north also. So the acceleration is in the same direction as this force. That's nice. But what is the other force on this object? So I know that there are two forces here. I don't know the direction of the other force. So we can just call this force FA and say FB is, I don't know what that is. So we can go back to Newton's laws and we can see that the sum of our forces is going to give us MA. So this sum of forces is just a fancy way of saying F net. My net external force on my object is equal to the mass times the acceleration. And of course these are all vectors. So what is this net force? Well, that's going to be these two forces, FA and FB. So let's just add those two guys up. FA plus FB is going to be equal to MA. And let's let this north direction be positive, and then whatever turns out to be negative will be to the south. So here I have FA. A is positive, it's going up. B, I don't know what it will be, but the algebra will tell me which direction it is. A is going up. So let's go ahead and plug in what we know. So FA is positive, so that's 20 newtons, plus FB is equal to mass by 10 kilograms, and is accelerating at 1 meter per second squared. So this is 10 newtons, so I can write that out pretty easily. So 20 newtons plus FB has to give me 10 newtons. So FB has to be minus 10 newtons. So what's my direction here? I know FB actually should be some kind of vector. So this minus 10 newtons, or I can do 10 newtons to the south. So I know that FB has to be 10 newtons to the south. So that now I can look at this again and make sure that everything looks correct. So 10 newtons to the south plus this should give me 10 newtons to the north. And that 10 should be equal to 10 kilograms times this acceleration. Here we have a truck. Here we have a truck that has an acceleration of 2 meters per second squared. So let's go ahead and draw my truck. Alright, and it's going to be accelerating at 2 meters per second squared. It's really hard to write it too. What would be the maximum acceleration of this truck if, so I really have two problems here that are related in some way. So what is A? That's what I want to find out. If it's towing a trailer with 3 times its mass. So here the truck has some mass, MT. Here's the truck's mass, MT. And then the trailer has a mass of 3 MT. So in this case, some force has to be applied to this truck to make it accelerate. Otherwise, it'd move at a constant velocity. So I know that F net has to be equal to mass of the truck, acceleration of the truck. So that's mass of the truck times this 2.0 meters per second squared. Now I don't know the force of the truck that's provided by the engine or whatever. Now let's look at the second case. Here I have the net force that's provided by the engine of the truck. And I know that these two have to be the same because I'm not changing the engine in this truck. I'm not changing anything else. I'm just attaching a very heavy trailer to the truck. It is equal to the mass of this whole thing. So it's going to be 3 mt plus mt times the acceleration. And that's what I want to find right here. So this is equal to 4 mta. So since the truck's engine isn't changing, these net forces have to be the same. So I know that mt times that 2 meters per second squared has to be equal to the 4 mt. So that's the total mass trailer system times the acceleration of that whole system. So I can find out that that acceleration is going to be 2 over 4 or 0.5 meters per second squared. So because I quadrupled the mass, I am having to divide this acceleration by 4 because the force provided by the engine has to be the same.